So because this all around, what you need to do is to sign, put your signature. Alright. So we are going to have our third module of the day. We'll talk about overview of oil extraction, and we have a speaker, Mr. Qua Kiat Seng. Qua, I consider him as a veteran, of the industry, oil and fats, very famous guy, in the industry, respected, very interesting career, in the oil and fats industry. So I will let him talk more about himself. Okay, so over to you, Mr. Qua.
Okay, thank you very much, welcome. Over-introduced. Okay, anyway, this is going to be a bit complicated, but I just want to summarize it in this way. I divide it in 3 sections of my life, because I'm so senior. The first part is when I actually was working in oils and fats processing, and that was from where? Until 2006, since 1974. So refining, foods, oleochemicals, personal care, Unilever, ICI, KLK, Malaysia, Australia, and Europe. Then after that, I retired. I went to Standard Soap to work for in the UK for KLK. After that, I took on part-time roles for UMG and for Popsic. So a lot of my contacts and the people I see here all are because of Popsic. And Monash has been a very strong supporter of Popsic activities until the pandemic. Okay. Then after that, I thought I retired but Prof Chan said, come back and lecture. So I ended up in Monash. Okay. So I was there for 2.5 years. After that, I said, I want to retire. I said, no, carry on. Now they make me a young lecturer. Okay. Alright. So that's the 3 phases of my life. Okay. So hopefully I am going to be really retired now, Prof.
So soon.
Not so soon. Okay. So what I'm going to cover is the following: the types of oil seeds. And it's, I think, can be quite interesting and complicated because I think there are at least 17 types of edible oils that we can look at, and then look at the techniques and how you need to pre-treat the oil seeds before you can start the extraction. And extraction is quite simple to divide into 2 parts: either mechanical or solvent extraction. Then of course there are some other considerations I just like you to know. Okay, so if we look at the oil seeds, Prof Chan already put all asked you to match the tree, the bush and the seed. Now I've got this just to show you the oil content in each one of them. It's varying amount of contents, and what is interesting is I just took this from Hainan Hua Thai cereals. The Chinese are making a lot of machinery now for oil extraction. So you can see the different types. Now, what you can see, I think 2 main things here. One is the palm oil. It has got a very fleshy mesocarp, and for some reason, I don't have olive oil here. They don't do it for olive oil, but it's got the mesocarp where you can literally press the oil out. Then you go to the extreme, to the other end. You see the rapeseed. It's here. Now, in Prof Chan's picture, it looks very big. Actually, it's less, about 1 millimeter in size. It's so small. Can you imagine how you're going to press it out? It can be quite difficult. So, if you look at these seeds here, they're all called seeds. They're all on varying sizes and so on, and varying levels of difficulty in extracting the oil. And the oil contents, they're also quite different as well. So we're going to approach this and see how we're going to extract the oil from these oil seeds. So the extraction techniques are divided into 2, which is basically a mechanical and solvent extraction. So you can do cold pressing where no heat is applied, or you can apply heat, and it's called hot pressing, and you can squeeze out more oil. Or you can use solvent extraction where you use organic solvents such as hexane, isopropyl alcohol, or you can use a supercritical solvent like carbon dioxide, which is a far cleaner process, but yeah, more expensive and difficult, expensive to do. But sometimes both processes, you squeeze out with a mechanical extraction, then the balance of it, you take it out with solvent extraction. So it's a combination that you use. Yeah. Okay. So expression, what is that? It's a process of mechanically pressing out the liquid that's inside the solids. Just press it out. Yeah. Okay. Now you can use a lot of equipment. It can be screw presses, roll presses, and mills, collapsible plate and frame filter presses as well, and hydraulic presses. Yeah, these are some of the examples. There's a very wide variety of equipment that you can use, but basically all it does is just press it out. Yeah. So what's the best way you can press it out? That's what we've been looking at. And then the efficiency of the mechanical expression, unfortunately, cannot be equal to 100%. Yeah. So in actual operations, it seldom exceeds 90%. But this is not necessarily a bad thing. The last 10% there is also useful to have it not taken out as oil. I'll explain that to you in a while, because Julian has touched on it a bit in his lecture as well. Okay, now before you can take out the oil seeds, you have to prepare. Yeah, you cannot just press it like that. You have to prepare. So what do you need to do to prepare? Yeah. So first thing is you need to clean the seeds. Yeah. And what you do is you need to remove foreign material, because when you're taking this up from the tree, from the ground, you've got the stem, the leaves, the other seeds that may mix with it, sand and dirt. So you remove this by screening. That means you put it through a screen and you filter it out, or aspiration by blowing air. Yeah. So that's the important part of it. And if you have got metal inside there like iron, you can use magnets to remove it. Yeah. So this is usually carried out before you start the extraction. Yeah. Because if you do a proper seed cleaning, this will reduce your maintenance costs, increase your capacity, at the same time improve your oil and meal quality. Yeah? So if you don't clean it up, the metal parts there will damage your screw presses and so on. Yeah? Because the screw presses, even without all this damage, you still got to change it. Yeah? It doesn't last forever. So the after the cleaning part, now you got the dehull or decorticate, because this the all you want is inside the husk. Yeah, the hull. So you have to break it open so that you can reveal the seeds that contain the oil. So that is called dehulling. And this is very important in order to get the good quality of oil and meal in color and flavor. Now you notice when I talk about extraction here, meal always come in. Yeah? Because quite often, because we're in Malaysia, we think of palm oil, we only look for the oil. But in actual fact, when you process most oil seeds, you also are very interested in the quality of the meal. So the normal way of dehulling oil seeds, of course, is to just crush the seed in the meal so that the hull will break and come off. And then the hulls and the meals are then separated by screening, air classification, and also by gravity separation. There are several steps you can do that, depending on how complicated it is. As a result of doing this, the moisture content will be lower by 1 or 2%. Yeah? And this will help the meat on the hulls to come out from it. Yeah? So it doesn't stick to it. You want it to come out as easily as possible. Okay? So this is the dehulling process. After that, you've got to crush the meal in roller mills to facilitate the following operations, such as cooking and extraction. So you need to crush it first. 1 or more pairs of rolls are used, which may be smooth or conjugated, yeah, depending on the type. And the rolls are usually in a pair. You can run at the same speed or you can run at different speeds. depending on what you want to get out of it. And if it's too intense, then you're going to produce a lot of fines. And the fines are no good because once you get the oil, then the fines will not settle. Yeah, it will stay in the oil, and you don't want that. Yeah, okay. So you got to be careful not to make it too fine. Okay, after that, you got to cook, or what they call conditioning the oil. Why? Because you have to subject the heat treatment, which is conditioning. Why do you do that? Well, there are a number of things you need to do. You got to break down the oil cells. You got to coagulate the proteins to facilitate separation of oil. You don't want the proteins to mix up with the oil. You want to reduce the oil sticking to the solid surfaces. You want to insolubilize the phosphatides, which I'll come to that. You want to increase the fluidity of the oil. As the temperature goes up, the oil flows more easily. You want to kill the molds and bacteria, and you want to inactivate the enzymes, because in some of the oils, the enzymes already start working the moment the fruit comes down from the tree. Yeah? So you want to stop it. And then at the same time, also dry the seed to a suitable moisture content. So the cooking process is very important to do a number of things. And these are very important things to do so that you get good separation of the oil. So that's just. Oh, yeah. Thanks. Okay, so the mechanical, let's look at mechanical extraction first. Yeah. Here for me to see. No, I can see. Okay, so the mechanical extraction is where it's a solid liquid phase process, a separation process, which is applied to the seeds, cooked seed flakes. Yeah, and now you have to make it into flakes as well sometimes in order to allow for it to be extracted more easily. So it can be executed either batch-wise, which can be hydraulic, which means you put a lot of pressure on it, or by continuous, and that is mainly mechanical working presses. Mechanical means they are moving all the time. And so this method usually uses an expeller press to give pressure on the vegetables, the nuts, and the seeds to cause the oil to run. Now, usually the mechanical pressing method will provide yields. In this case, I put down 65 to 70% of the oil. If you get 80%, it's considered to be very good already. So many commercial processors, they start with a mild pressing to take up 60-70%, and then take the rest out by solvent extraction. So you get the maximum out. Okay, now the first one is of course cold pressing, and this is a standard they've agreed to. If it's cold press, it means that the temperature does not exceed 27 degrees. Yeah? Okay. You might find that a bit difficult to do in Malaysia, but this started off, with the pressing, for example, olive and so on. And they would, for example, be pressing the olive in the morning before the temperature goes up. Yeah? So this is how the 27 degrees came about. So high oil containing seeds such as sesame and peanuts and the oily pulp of olives yield free oil by simply application of pressure. So sesame, you can press it out. Peanut, you can also press it out. Yeah, I know that the peanut oil that is used is very nice flavor. Is, for example, from Shantung in China. You roast it nicely, and then after that, they press the oil out. You get a very nice flavor. So quite often, this type of oil requires no processing. Why? Because the flavor is very important. You want the sesame to have the flavor, you don't process it. Once you process it, the flavor is gone. Peanut oil, same thing. Yeah? And olive, of course, the virgin olive oil is something that you don't refine. Otherwise, the peppery taste and so on is not there. Yeah? Okay. So you got olive oil. It has a very strong flavor, but well accepted by a lot of people. And of course, cold pressing is not very efficient because it's cold, so the oil cannot flow. Yeah, so easily. So that's the cold pressing. Hot pressing means that the all meals that it's quite often they combine it. All meals, seed residues from which the oil has been removed, obtained after cold pressing, can contain still a lot of oil. Yeah. So they have now developed more efficient presses, such as a hydraulic batch press or the continuous spiral press or expander. So this developed a very high pressure of about 150 to 2,000 bar, and as a result of that, it only leaves 4 to 5% of the meal of oil in the mill. So unfortunately, such processes, because of the high pressure and a lot of work it is doing, develop quite a high temperature. And when you do that, the oil will become dark, and then the oil seed proteins will be denatured. Now bear in mind that protein in the oil meals is very important because it's a feed for animals and so on. So you want to denature it. Okay, so let's look at screw press. Different type of oil expellers. This is a screw press. So the screw rotates within a cage of error, which is lined with a case hardened 2 steel bars. Yeah. So this is the press, and there are spaces between the liners so that allow the oil to come through. At the discharge end, yeah, this is the choke. At the discharge end, you can have a choke there. You tighten this so that you can increase the pressure by tightening the space over there. And then the choke is typically adjusted by a hand wheel. This is a manual one. And the heat generated can be dissipated either with the cage that's outside or within the annular space inside. You can have cooling water so that it is not so hot. What I just wanted to point out to you is that you all get all these slides. How many of you have downloaded the slides? And the rest, not yet download, not yet read. We were hoping that you will read and ask a lot of questions. So now I know who are the students. Get extra points about Prof. Chan. Yeah. Now, Sean tells me that some of you who go and download, when you click the link, it says ask permission. So you have to ask him for permission, then you download. So don't give up. Yeah? This is to restrict the use of it. Okay. So you guys are getting these notes, so you can refer to it. Now, what I wanted to do in my slides, some of you after this course may want to go and do more advanced things and so on, and you want to read more. So I give you some references so you can go and refer to the sources. Yeah. So like this one there, I purposely put down there. The source is from Gan and Hannah, yeah, 1983. So you can go and search for it and find more information about this manual screw press. Okay. Now I managed to find a screw press for you. This is actually not for oil, but it was for drying some water sludge. Yeah. But the principle is the same. Yeah. This is a relatively simple process. You feed in the seeds here, and then the screw will screw it out. And what happens is then the oil will drop down here, and at the end here, after adjusting the pressure code, which is the choke, the cake will be discharged here. So this is a very simple process, low capital cost, and no solvent is used. But it has its drawbacks. There is it's low capacity. Quite a bit of oil is still left in the cake here. Yeah. And requires a lot of power, and depends a lot on the operator and how he operates it, how he adjusts the pressure code and so on. Yeah? But this is a very simple one that you could use as a starting point. So how does the material flow in the screw press and the effect of the variables? So just to show you, this is a picture of a screw press. Yeah, they have opened it up so you can see the cross section of it. And so what happens in the screw press on the right, you can see what goes on. Have I got the direction right now? Yeah. So you feed in over here. Yeah, the screw press is turning here. This is the feeding zone. Then the seeds are transported to the screw, and then the air is pushed out. This is the transport zone. In compression zone, the seeds start to get crushed, and the air contained in between the seeds is expelled. then the seed mass is compressed and the oil extruded. So this is the exudation zone. Finally, the pressure is released and water is vaporized because of pressure release. And then the meal expands, and this is the expansion zone. So this is what happens inside the screw press. Okay, I'm going to look at one which is on the press room flow for soybean. Yeah, soybean is pretty important, so I picked it up. Now you might want to refer to Bailey's Industrial Oils and Fats Production. I've taken this from 7th edition, volume 5. Yeah. This might be a bit daunting for you. When I first started work in 1974, we had Bailey's Industrial Oils and Fats as a Bible. One book. Today, 7 books. It's expanded so much, 7 books. So you got to pay quite a lot of it. But I think in Monash we can access the e-version. We're also very proud to say that at least one of our lecturers has contributed to Bailey's. Yeah, palm oil section. She's a co-author inside that. Okay, the older version was MPOB did the contribution, but the new version is other people. Okay, so this is the press room. First thing is, yeah, so complicated. I try and sort it out for myself and sort it out for you. The meal comes inside. Sorry, the seeds come inside. It is cleaned over here. And then after that, it moves on to, let me see, number 2. It goes on here. There's a magnetic separator to take out the stones, the iron, and so on. Yeah, and it goes on to the cookers on top of the mills, of the expeller, the presses. Yeah, where it is pressed. After that, it is screened to remove some of the what do you call it, the solids. And then it is heated up. Then the unfiltered oil is here. It goes to a filter press, and then the filtered oil goes out to storage. Then the meal that comes out goes to a cake bin where it is cooled, and then after that it is back off as bags. So you can see for soybean, for example, this part of operation is very, very important as well. Yeah. Okay. Next one. Hydraulic press. This one is so simple to explain. Yeah. You can see there, there's a drawing of it. It's got iron plates there. So you pack the all seats inside there, and then you start the hydraulic press, presses it out. Or I think this one goes from bottom. It goes from bottom up, presses the oil. Yeah. So it consists of a series of horizontal corrugated plates, and it's separated by pre-molded cakes. So either you put them into bags or you arrange them nicely. And then it's accomplished in 2 steps. Step 1, 50 bar for 15 to 20 minutes. After that, step 2, press even more, 280 bar for 5 to 10 minutes to complete the whole expression process. So how fast you can do this depends on the size of the seeds, the size of the hydraulic oil press, and also the seeds that are being pressed. Yeah? But as you can see, this should be a very old-fashioned way. Yeah, still from Hana there. Okay. Then I like to talk a little bit about olive oil extraction, simply because it's got quite a lot of similarities with palm oil. Yeah. Okay, this is the olive seed. Yeah, and then this outside here is the mesocarp where the oil is present. Inside here is all hard stuff, and there's no oil inside there, it's just stone. Yeah, very hard stone. No use on. That's why palm oil is so special. The 2 oils in one. This one only got 1 oil and 1 stone. Yeah. Okay. So first we're going to do the olive oil delivery and scaling, and then defoliation means take out the leaves. Afterwards, you'll have a video to see it. I managed to get one from National Geographic. Quite old, but it's still very easy to understand and see. Then after that, you've got to wash it. They actually wash with water. Wash the olives. There's an important reason why they wash the olives, because you don't process it anymore after that. The extra virgin olive oil, you can literally drink it. They call it a fruit juice or not? You drink it as though it's a fruit juice. Yeah. Okay, then there is the crushing and milling. You've got to crush it first, so crush this out. And then maxillation means that you need to mix it. After that, you apply the pressure. Yeah. And the olive pomace all will come out together with wastewater. And you still recover from the olive pomace. This is the last 5%. What they actually do is to extract this with solvent. Then the olive is pressed, and then the olive oil and residues are here. And then you've got the separation in the wastewater, and then the clean olive oil comes out. So this is the process flow, and you can look for it in Bailey's in volume 2. Yeah? So the information is there. Now what is interesting is, you're going to watch the video in a while. I managed to find the particular machine that we're using inside the YouTube. Yeah? And I think this decanter, most of you in the pharma industry are very familiar with it. Yeah? If you look at it, I think you will recognize it. So Prashant, can we play the YouTube video? It's just about 3 to 5 minutes.
Macam betul je kan? Cerita sebenarnya. Kenapa kita tak rambut tebal dan ketat, kalau tak dijaga, rambut boleh gugur. Dove Micellar Baharu kini mengandungi vitamin biotin untuk rambut 10 kali lebih kuat.
For the health-conscious gourmet, there's one ingredient that's sure to set the taste buds sizzling. From frying to salad dressing, olive oil is an essential in any modern kitchen. A wide variety of grades and flavours are available, but they all have one thing in common. No, it's not the green bottle it often comes in, but the olives themselves. Each type of olive has a unique taste. By combining different types, the producer can create an oil with an individual flavour. The process begins at harvest. The traditional method involves collecting olives using tiny rakes, but it's not very efficient. For a big crop like the one on this farm, an automated harvester is used instead. The machine surrounds each tree and literally shakes the olives off the branches. The fresh fruit is collected into a waiting hopper along with some leaves and twigs, but these can easily be removed later. A machine like this can collect as many olives in an hour as it would take the traditional farmer to collect in an entire day. When the harvest reaches the production plant, the fruit is washed to remove any dirt, leaves or twigs that were caught up in the collection process. The more stubborn twigs and branches that remain are filtered out using a grill, which only allows the fruit to pass through. To get the best quality oil, the fruit should be pressed as soon as possible. Traditional methods mean there's a delay between harvesting and the grinding process. The original method also uses big millstones like these granite wheels to grind both fruit and the stones into a thick pulp. But modern production carefully controls two vital factors. First, the fruit is sent directly from the harvester to the grinders with as little delay as possible. And second, the fruit is ground more gently. Olives can lose flavour if the fruit is heated by the friction of grinding. The most sought after olive oil is called cold pressed. If the fruit pulp goes over 27 degrees, it can no longer be called this and loses value. It's time to extract the oil. In the traditional system, the pulp is layered between hemp mats. Each quantity of pulp is followed by another mat and so on, until the alternate layers look like a stack of giant pancakes. The stack is placed in a hydraulic press, which literally squeezes the oils from the pulp. It's collected below and has the traditional cloudy golden colour associated with good quality olive oil. The modern method is far less aggressive, but just as effective. Instead of crushing the pulp, it's spun in a centrifuge like this one. As it's spun around, the oil passes out through a fine mesh, leaving the pulp behind. The oil can then be siphoned off and stored, while the remaining pulp is collected elsewhere. It's not wasted though, it's recycled and can be used as fertilizer or animal feed. It may surprise you to know that once it's been pressed, olive oil can be tasted like wine. The experience is obviously very different, but this is one way the experts can assess the purity and flavour of their product. Pure unfiltered oil is considered the most valuable. If the residues are filtered out in a centrifuge like this one, what emerges is considered a slightly inferior grade of oil. The standard grade that you would find on a supermarket shelf is stored in steel tanks like these. Here, the final residue sinks to the bottom, and what's pumped out at the end is a clear olive oil for the mass market. Olive oil is usually bottled in green glass, and there's a good reason for this. It helps filter out harmful UV light that can cause it to deteriorate. Finally, the bottles are sealed and labelled up, ready to be shipped out to homes and restaurants all over the world. So whether it's cold pressed extra virgin for dressing or standard grade for frying, olive oil continues to be cooked up in kitchens everywhere.
Okay, I have to relax a bit. Yeah, but I think it's very interesting. It's quite old, but I think you can see a lot of things, because what's nice about this, it goes back a little bit, so that you know the history of it, how this is extracted, yeah? So that you can have an idea of what pressing is like. So one of the things that you saw was the like the rumpa like that, the big wheel that we use to grind our sambal, chilies and so on. Yeah, they're using that. So what they do is early in the morning, before it gets hot, they roll it. That's called the first press before it becomes hot. After that, I think it's the second press. But this term, first press, second press, all that is traditional. Yeah. So tomorrow, when you listen to audio chemicals, they will talk about first press, stearic acid, second press, third press. You will understand that this comes from the tradition. Yeah. Okay. Of pressing once, pressing twice, pressing 3 times. Yeah. Okay. So this gives an idea, and I think most of you will see some relationship with palm oil. So I hope you can relate to that. Okay, so the other one is solvent extraction, and the basic principle of this is you use non-polar solvents. Yeah, water is a polar solvent. You use non-polar solvents. So basically, it is a solid liquid extraction again, and the transfer of oil from solid to the surrounding solvent oil solution. Once it comes out into the solvent, the whole thing is called micellar. So it involves 3 steps. The first step is the solvent has to get into the solid. After that, the oil droplets dissolve into the solvent, and then after that, the oil has to come out from the solid particle to the rest of the solvent that's outside the solid. So this is a 3-step process. What you do with solvent extraction. So got a very nice drawing here. I won't go into too much detail. You will be able to get the extract of it, but basically just run through quickly. The seed, when it comes in, you're going to clean it up and dry it, and then after that, the hulls, you're going to take out the hard shell, yeah. And then after that, the kernel that comes out, you can steam it if you need, if it's a low oil. And then what you do is use the screw press to press out the oil for refining. Then the cake can go into pelletization and flaking, or you can get it out by direct extraction and still send it for pelletization and flaking. Now this extraction process is where you feed the solvent in. You can use a continuous belt, horizontal basket, Hildebrand or Bowman extractor is used. I'm going to go into that into detail because it's very interesting from a chemical engineering point of view. Yeah. And then the meal that comes out, there's 30 to 35% solvent. You go to a desolventizer. That means you take out the solvent and then you get the meal. Yeah, okay. And then the meal will be the for animal feed. Now the oil and solvent will come out directly from here, and then you flash it. You get the solvent, you recycle it. The oil, you further steam strip it to remove the balanced solvent, and then you get the solvent which you can recycle. So this is outline of it. What is I like to point out that's interesting is, this book where this is got from is called The Principles of Mass Transfers and Separation Processes. So if you are looking for all vegetable extraction, you won't find this book. And our friends from Petronas who might be interested, Dr. Dutta was a lecturer in UTP when he was writing this book, because it's a principle of solvent extraction rather than focusing on vegetable oil extraction. Okay, so you can find the book quite easily, I think. Okay, so what are the factors that affect solvent extraction? The first thing is you need to have, if the structure is porous, that is better, because then the structure allows the diffusion for the solvent to go in, and also for the solvent to pass through the solid material. And then if you cook it flake it, you can increase the porosity. So the solvent must have a higher solubility, is preferred. That means the more oil it can absorb, the better. Then you want a low boiling point so that it's easy to separate it up, so you don't have to heat it too much. Okay. And the rate of extraction can be increased by increasing the temperature, as we know. And higher temperature means the oil is more soluble, higher diffusion coefficients, and lower micellar viscosity. This can flow much more easily. Okay, the choice of solvent. What sort of solvents should you choose? You should have good solubility of the oil. You don't want it to solubilize non-oil components, and it should have high volatility, that means low boiling point, so that all the solvent can be removed from the micellar and also the meal by evaporation. So for example, hexane is quite a common one to use because it can be removed quite easily. Now you don't want it to be too low, because sometimes your process is a bit high temperature, you don't want to lose the solvent. And finally, it should be low viscosity. Okay, then low latent heat, so that you don't use so much energy to recover it. Low specific heat, so again, don't need so much heat to keep it warm. Chemically inert, that means it should not affect the oil and the seed flakes, and it should not be toxic, carcinogenic. But there's always a question whether any solvent in itself is not carcinogenic, and it should be non-inflammable, non-explosive, non-corrosive. Sometimes quite difficult to find. Quite a lot of solvents are flammable, and you can buy in large quantities at a low cost. So when you compare the solvent extraction process, what's the advantages? You can get more oil out of it. Production cost is lower and requires less time. But compared against a mechanical process, that is cleaner and higher in natural colors and flavors. And it can meet large, you don't need large volumes of solvent, and the construction cost is higher, and for refining as well. High maintenance cost, and then less residue oil in the meal. That means you have extracted too much oil out, you don't have enough oil in the meal. You still need oil in the meal. Okay, next one. Okay, types of extractor. Most simple one, there are two types, batch and continuous. So, the batch one, just a batch there. You put in the seed, put in the solvent, stir it up, and then after that separate it out by dropping the micellar and then taking the meal out. So this again from Dutta. So you put in a certain amount of flakes and then you just take it out and drain. So very simple process, but very labor intensive. Then of course there's the continuous type. Both are fed into the extractor. All seeds and solvent are fed at the same time. And then the different types, depending on how it is used, how the solids and solvent move, is what you call it. So there are two types. One is the percolation. Percolation means you just drop the solvent on top of the flakes. Immersion means the whole thing is soaked inside there. So let's have a look at the types. So the continuous extraction, the percolation method, it trickles to the bed of flakes, but it doesn't fill the void completely. And then a film of solvent flows over the surface and then removes the oil which has come out from inside. So this is preferable when the resistance of the to diffusion and so on is low. Yeah. But immersion method is totally immersed in a slow moving continuous phase of solvent, and it works better when you have material that the oil is difficult to come out from inside to the outside. So if there's a thick particles or dense tissue. So this is the vertical Bowman basket. Yeah, what you find here is that the pure solvent comes in here. This is the upgoing basket. These are baskets with perforable trays at the bottom so the solvent can flow through. So it goes in this direction. And then here, this is the ready, this is fresh cake. The fresh cake comes down here and goes round. This is the pure solvent on the spent flakes and drops down here. And then this is the this half micellar. This is a compartment here. The half micellar will go up and pump and put over the new dry flakes. Yeah? And then here they extract out the full micellar. So this is the Bowman extractor. Yeah? So it's continuous. It goes round and round. Pure solvent here, half micellar comes up here, full micellar comes up and forth. So this is how this one works. Yeah. So you can see people have spent a lot of time working out this. And this is not the last one, there's still another one. This is Hildebrand. This is a U-shaped, what do you call that? Screw conveyors. Goes this way. So they feed in here. And then the solvent goes in here, so this is sort of a counter current flow. Yeah? And then all the solvent comes out the other side. So this is the Hildebrand extractor. Next one, horizontal basket extractor. This is a horizontal basket that goes round and round. I think, yeah, this is the direction. So the seeds come in here, drop into the baskets, and then the micellar that is recycled is pumped in here, but the fresh solvent comes in to the spent already, where the seeds have been half extracted already. And then all the solvents drop down here, and here the full micellar is taken out. Some of it is recycled, as you see there. And then the seeds are discharged over here. Okay? So this is the way of doing it. And then there's another one, rotor cell. This is circular. This goes round and round with the beans, the bean flakes being fed here, and then it goes round, and then the fresh micellar is sprayed into here, and there's many stages. This is the interstage. Liquid is pumped out into it. Fresh hexane comes into here, and then the least solids come out here, and then all the micellar comes out. Yeah? So this is another way of doing it. So there are lots of different methods of taking out your oil. Then the micellar contains 30% oil, and you got to excess solvent must be removed by distillation. Yeah? So characteristics of good energy economy, minimal heat damage, minimal solvent losses, efficient removal of large traces of solvent, and good operational safety. Most of solvent evaporation includes flash evaporation, which is the simplest, just flash it, vacuum distillation, and steam stripping when it's more difficult. So you have to filter the micellar when it comes out because there are solids there. If you allow it to be there, it's going to make problems for you downstream in the pumps and the pipes, heat transfer equipment, and so on. Yeah? So you can remove it. You can remove it by filtering. Yeah? Okay, the meal also contains solvent about 35%, and you're going to remove this very critically because in the end it determines the quality of the meal that you are feeding to animals. Okay, so this is the soybean hexane extraction plant. Again, you see a layout there. I'll just try and take you through very quickly. The grain comes here. It goes inside the P2, which is the direct extraction preparation of the meal to make flakes. After that, this M here is the one that handles the meal. And then this is the solvent extraction part. and then after that they evaporate and take out, recover the solvent, and then the finished meal goes into storage, and then the oil comes out here. So it's actually a very, very big operation. Again, you can take it from ladies. This one, of course, is very exciting because what it does is it makes use of supercritical fluid. In this case, it's carbon dioxide. So basically, what you do is you heat it up, apply pressure to carbon dioxide, and use it to extract the oil. After that, you cool it down and expand the pressure. The carbon dioxide is released. The oil and the meal comes out clean. There's nothing with it. So this is quite a nice operation. But usually it is done as a batch because it's more difficult to feed the solid and remove the material continuously. Yeah? So this is the one using supercritical fluid. This is our lab. Okay, finally, just some other considerations when you are operating an extraction plant, what you should bear in mind. First thing is process safety. Yeah? There will be a lot of dust from the seeds, the meals, and the alpha toxins in the raw materials, especially from groundnut, for example. And then the grain silos, you've got to be careful of dust explosion. Or if you go in the silo, there will be a lot of nitrogen oxide and carbon dioxide in there, so it shouldn't enter the silo. Now, as Dr. Julian said, all seeds can be stored for a long time in silos and so on, not just in bags. And you've got to be very careful about entering these silos. Or you've got to be careful that you don't get dust explosions in these silos. Yeah? So then when you convey these seeds using elevator belts, you be careful of the dust and the static electricity as a result of it. Yeah? Now, when you are extracting the hexane solvent, the hexane, you've got to be careful that there is adequate ventilation so that you don't accumulate that and there can be an explosion. And then you can properly distill the oil after extraction so that the solvent is removed. And now this is very common. Everybody will see this. Usually, extraction factories are very, very oily and slippery. But I wish there are all extraction factories that are not slippery. I think it can be done. I can have an argument with people about how clean you can make it and how safe you can make it. Yeah? And then, of course, the injuries caused by unprotected machinery, moving parts, and conveyors. Quite a lot of mechanical processes in water, so that's why you've got moving parts over there. Okay. So this information.
In the morning,
I go remind them when I go on the way. Okay. Dim the light now, or I want to keep it this size first? I go dim the light, then I go remind them.
where's the attendance list? Have you collected it?
Yeah, got there are still two participants haven't the two from Kona.
Do you know? Do you have the list?
I can go and look for them. I think they're over there.
Yeah. Okay. Probably if you know who they are, you just ask them to sign.
Sure. I dim the light.
Okay. Recording rate.
Yes, running.
Still got people outside. Yeah. Should wait for them.
Sean, please let me.
Yeah. Sweets? Yes? No? Yes.
Treats lah. Macam sponsor.
So now we'll continue to the next module. Welcome back, Mr. Qua. So he's going to talk to us about overview of refining. Mr. Qua.
Yeah, thank you, Prof. Chan. Yeah, I'm not going to show you the next one. You can see you've seen it before. Yeah. What is happening is this is we finished all extraction. Okay, you've seen the overview of oils, and then Hema came in, and now you know about palm oil extraction. So now we're going to move on to the next part, which is refining. So this afternoon, it's the very last lecture, I will talk about overview of refining. Then tomorrow morning, we're going to hear about refining of palm oil and palm kernel, and also on fat modification. Yeah. So that is going to be done by a super person. Yeah. Okay. Keep that a secret first. Yeah. All right. Now, one of the things during tea break and so on, we met quite a few people around here, and one of the things, of course, we suddenly realized that many of you are actually experts in some particular area or more than one area. Yeah. So I would ask that if you know the answers to some of the questions that people are asking, please feel free to join in as part of the panel, because I asked the same thing of our lecturers and speakers as well. Yeah. Okay. So don't be shy. If you know the answers, please share with us. Because some of you I know are experts in your area. We may not be. All right. So you can participate some more. No need to be shy already. How many days already? No, how many hours already? Okay. All right. So let's start with the refining of oils. Okay. What I'm going to try and cover is, why we do refining. That's the objectives of it. Then there's the chemical refining process, as you know, and then the physical refining process, and finally have a look at one or two other considerations that we should bear in mind. Okay. So what's the objectives? Why do we need to refine? Yeah, there are a few reasons for it. First one is to remove the free fatty acids. So there's all sorts of levels of free fatty acid, except for those products where you are keeping the flavor and so on, and you can keep the fatty acid level low. Then you don't need to refine and remove the free fatty acid. You've got to remove the phospholipids and any products that has been oxidized, the metal ions that are there, the color pigments, and other impurities. So you can see that the refining process can be a very important one, and of course we try and remove as much as we can. But on the other hand, those who are refiners will tell the people who are supplying us raw materials, don't put in any rubbish. We're trying our best to remove it, but don't put rubbish in. Yeah? Okay, so preservation of valuable components now. One thing is that a lot of oils actually have got vitamin E in them, so we don't try to preserve that. And others have got tocopherols, natural antioxidants, as well as other minor components like sterols, sterol esters, tocotrienols, and squalane. So we want to try and preserve that, because the refining process quite often will remove this, unfortunately. Yeah. Okay. And while we are doing all this, it's important that we minimize the oil loss. Yeah, we don't want the oil to be lost. I'm trying to get wrong one. Okay, we're trying to minimize the oil loss, and finally, as we do carry out the process, we want to avoid the oil being degraded, because one of the things we are doing is quite often the processes are done at a higher temperature. So we don't want to make sure that the quality deteriorates. Okay, this is a very nice slide. I think it may come from Fuji oil, I don't know. Fuji oil, is it? It's here. Uni Fuji is here. I don't know whether I'm choosing this from you or not. But I thought it's a very nice slide, because it does put in the form about trying to refine the oil and to take away all these things you don't want, and finally you get the refined oil. Yeah? So that's what this whole refining process is about. And So one of the things is, the reason why I choose this picture is they put the oil as green color. Yeah? Because many of us don't think of the crude oil as green in color. When actually there is a green color inside there. But we'll look at that in a while. Yeah. Okay. Then there are also non-triglyceride components that's present in what do you call that, in crude oil. So I call this NTG. So I need to add the word N-TAG to Prof. Chan's lecture. Remember, I was telling you about TAG. Now this is the N-TAG. So what are the major ones? Very big amounts. Free fatty acids. Yeah. Phospholipids, gums. Very, very big component. Huh? Then as a result of the free fatty acids being formed, you get the DAG and the MAG. Yeah? So thanks to Prof. Chan, now you already know all this. I don't need to explain that anymore, okay? Then the major ones there, the minor ones, tocopherols, which are vitamin E's, sterol esters, tocotrienols. It's only, interestingly, only present in large amounts in palm oil, I think about 1,000 ppm, and rice bran oil, about 600. Surprising, most of the time we don't know that there actually is tocotrienol. And tocotrienol is, just for simple explanation, is the more super antioxidant than tocopherols. Other compounds, yeah, and I put asterisk there. There's actually chlorophyll that you want to remove in rapeseed, soybean, and olive oil. Yeah? Otherwise, we always think of color as carotenoid, the red color of palm oil and so on. But actually, there are other colors there. Then all the commercial products, yeah, it always will be there, depending how you take care of your raw materials. So polar compounds, polymers, aldehydes, ketones, yeah, all sorts of volatile and non-volatile compounds. So I think you all know already, but this is just to refresh. There is the physical refining method and the chemical refining method, which is alkaline neutralization. So which can be both batch and continuous. So I pinched this chart from Alpha Lava, and there's physical refining and there's chemical refining. It's quite easy to see that physical refining, you need to decome, de-wax if necessary, bleach, and then the process of de-acidification and deodorization takes place at the same time and get edible oil. Chemical refining, you need to do a water gumming where it's necessary to remove the gums and produce crude lecithin where it applies. Alkaline neutralization with caustic soda, you get soap and you split it, you get the acid oil. De-wax, bleach, and then deodorize, you get edible oil. And what you get from the physical process is the fatty acid distillate. Thanks to Hema, you know that very well. It doesn't come from a palm oil. Okay? Next. So let's just start with chemical refining. Yeah. I have taken this chart, half of it, there's actually another half here, which is physical refining. Yeah. So what I wanted you to refer to is this source, AOCS. You can get a lot of information on the internet. I'm sure a lot of you have used this, but if you haven't, go into that. You get a lot of free information from there, up-to-date information, very useful. Yeah? So make sure that you take this down as a source. It's sometimes technical, sometimes commercial, so you can make use of it. So the chemical refining process is basically you have to degum to remove the phosphatides, you have to neutralize to remove the free fatty acid, and you bleach to remove the pigments. And then deodorize, the whole purpose of it is to take away the odors and the flavors. And the free fatty acids can be removed as well at the same time. And sometimes you need to do winterization for separation of the waxes. Yeah? Because some of the oils, especially those soft oils, I heard that customers like to keep it in the fridge. And you need to make sure that all you keep in the fridge don't become cloudy. which is a very severe test for our palm oil. Keep in the fridge. Yeah, I don't know why they keep in the fridge. Maybe because as Prof Chan said, because it's polyunsaturated, it's not very stable. Okay, all right. So that's chemical refining, and one of the most important things is gums, phospholipids and phosphorus content. Now, for us, when we are dealing with what do you call that? Palm oil. Is that palm oil? Yeah, palm oil here. You can almost ignore it because it's almost not there. Yeah. But if you look at the other oils, crude soybean is 1 to 3%. Yeah. And then there's another one, cottonseed oil, 1 to 2.5%. So can be very, very significant amounts. Yeah. So soybean is 1.3%, and therefore it's quite an important product. And as Prof Chan has shown, there's a bottle of lecithin there, isn't it? That he showed in his chart. Okay, so let's look at the water degumming first. So the first thing is, what is the purpose of degumming? Now these phospholipids are actually very, very good emulsifiers. And so if you don't remove it, when doing alkaline refining, it's going to emulsify everything, and when you do that, during the alkaline refining, you form soap, it emulsifies, you're going to lose even more oil. Yeah? Okay? And then if you leave the gums inside, the oil actually will become brown when you do the deodorization. As you bring the temperature up, you get the oil turning brown, which is something you don't want. And then it can form salts with copper, magnesium, calcium, so that the oil starts to degrade even faster. Yeah. Now, certain phospholipids such as lecithin will find very widespread industrial application. In fact, it's a very valuable byproduct. So you want to remove it because it's very valuable. Yeah. And the gums are two types. One is hydratable. So just by water washing, you remove it. But there's another 10% that's quite difficult to remove, and you require usually the use of acid to convert it to a hydratable gum to remove it. So there are several degumming processes. Yeah, I won't cover all of them, but just mention so that you know it exists. Water degumming, very common. Acid degumming, also very common. And of course, what is quite new is also enzymatic degumming. Yeah, and then there's also membrane degumming. So for water degumming, what you do, yeah. So this is just the layout of it. So it comes from Alpha Lava. And what again I like to point out to you is this reference book that is quite useful from Gupta. Yeah. And this one actually is specific to vegetable oil processing. Yeah. So it's a good source, and if you want information about processing, not only for my lectures, but for the other sections as well. Yeah. Okay, so water degumming, what you do basically is to heat up the crude oil, mix it up with water, which is added here, and then in a reactor. After that, you separate it in a centrifuge. You take out the gums, and then the oil will go on. You heat it up, and then you dry it. So basically, that's what it is. Yeah. Okay. So those are the process conditions. I think you can read that. So I won't go into that. So what is important is that extracted gums can be processed into lecithin for food, feed, or technical purposes. So lecithin is a very important emulsifier. I think I first came across it in instant milk. I think they add a lot of it inside. Remember in the earlier days when you had to make soap, what soap? Milk powder. You beat and beat and beat, I think it won't. But then the instant one came, you just add water and it dissolves. So it's a very, very important component. Not only in milk powder, but in a lot of other foods as well. Yeah. So this is the water degumming. The next one is the acid degumming. And for acid degumming, there are two processes. One is a dry one, and another one is a wet one. So the dry one is the one that we can use for processing oils with low gum. Palm oil, coconut, or animal fats don't have much gums, so you can use that. And so you add acid to the preheated oil, and then in this case, the gums will go into the bleaching earth and then you separate by filtration. Yeah. So what is so nice about this is that it doesn't consume a lot of energy, investment cost is low, and it's environmentally friendly because you don't use water, no wastewater, no soap stock occurs. So what does it look like? No, sorry, this is the next one. Wet one is for those with higher amount of gums. So like the corn oil, not as high as a soybean, but still high. So they are processed in the same way as acid degumming. However, to do gum hydration, water is added following acid apportioning. So these gums are removed by a separator prior to bleaching. And then it is beneficial because you use a centrifuge. It's easy to separate the gums with higher non-hydrable gums. So rapeseed and soybean is one of those. So the consumption of bleaching earth is reduced because the oil already has been extensively degummed. Yeah, so that's why it's important to remove it. So this is the acid degumming process. So I just showed what is here for the wet process. So the crude oil is heated up, then it is mixed with the acid. After that, it is water is added and it's mixed again. This is an intensive mixer. Stays in the reactor, I think, for about 30 minutes, and then after that, centrifuge it, and then the gums go out, and then it goes to drying storage. So this is the sort of temperature that you use, 60 to 70 degrees, about half, 0.05 to 0.2% of phosphoric acid, and deionized water. So you can see the use of phosphoric acid here. Enzymatic degumming, yeah. This one uses enzymes, and what happens is that yeah, this is a crude oil. You heat it up, then somewhere it's more for me to see. Somewhere at the enzymes. Is it here? Mixer, cooler. Oh my goodness, it's so small. Okay. Lost it here. Here, sorry. Here's the enzymes. Add the enzymes here, and then after that, you get it mixed, then you let it stay, and then after you pump it out, centrifuge it, and then you take the gums out. Yeah. So it is this is an enzyme solution, which is aqueous solution of citric acid, caustic soda, and enzymes. Yeah. It's dispersed into the filter oil at a low temperature, and then a high-speed rotating mixer, yeah, is used to mix the enzyme and oil solution, and then it can convert the non-hydratable phospholipids into hydratable because of the enzyme. So this is an enzymatic process. I just showed the Easy Max process, which was pioneered by Lee. But certainly, I think certainly San can tell me more because he was working in Novozymes. I think you do a lot of this as well. Yeah. Okay. Right. So anybody ask questions about enzymatic degumming, I know who to send them to. Yeah. Okay. We got all our experts here, no? Yeah. Okay. So it has benefits because it can provide a higher yield of and increased yield of triglycerides as well. Reduce neutral loss, reduce oil loss, and reduce the oil content in the meal for feed. You need some oil in the meal for feed, but not too much. Lower cost, operating costs, allows the physical refining because then you've got lower residue, lower phosphorus, and you can, especially for soybean, it seems that you can degum crude oil for very, very poor quality beans. So probably these are beans that are not good quality or beans that have been stored for a very, very long time. As Dr. Julian mentioned, you can store this for years. Yeah. Okay. And then you don't need a lot of water. Yeah. So you reduce the amount of wastewater there is. So now let's just go to the chemical neutralization. Yeah. It is used widely for vegetable oils. Yeah. So it is first pre-treated with phosphoric acid, then neutralized with caustic soda. It reacts with caustic soda, produce soap. The soap is separated, yeah, in the centrifuge. and then remaining soap is removed in a water washing and separating the oil and water in a water washing centrifuge. So it can be used for quite a lot of oils for refining. Soybean, gum soybean, canola, corn oil, cottonseed, and sunflower. So a batch process will look like this, and you have the vessel there, just a vessel there, and then you would connect it to a vacuum system, put in, there's a possibility for putting in the bleaching earth and so on, the dispersion ring for the I think it's for caustic soda, yeah, and then baffles there, and agitator, and then you circulate this. Okay. So it's heated about 80 to 85 degrees, and 10 to 15% deionized water added, agitate it, and then after that, water washing and draining steps follow to remove the soap. Then the oil is treated with 1 to 3% activated clay, bleached under vacuum at 110, 120 degrees. And then at the end of it, the FFA and phosphorus content should be 0.1 to 0.2% for FFA, and then less than 5 ppm for phosphorus. So this is a vessel that we use for both bleaching and for neutralization. A continuous process is given here, and I sourced it from Alpha Lava. Yeah. So basically, you look at it, it will undergo a series of process. The crude oil comes in, it is mixed with the acid, goes to a mixer. There's some retention mixers, but in the process, water is added. Yeah. And then after that, heated up, separated, and take out the soap stock, wash it here, and after that, in a mixer, mixed, and then after that, separated over there. After that, it's sent for drying. So if you use this technique, yeah, you can reduce the phosphorus level to less than 20 parts per million after water washing. Yeah. Okay. Now we come to cover the bleaching of oil. So it is a process where you would remove impurities with help absorbent, and usually this can be bleaching earth, but it can be carbon as well. And the impurities and the active sites and absorbents are attracting each other by van der Waals force of attraction. So the amount of attraction depends on how much electrostatic force there is between the impurities and the absorbent, the size of the component, and how well you mix the oil and the absorbent together. And also important is porosity of the absorbent, yeah, so that it can absorb it inside, and also the area of the absorbent. Of course, the larger the area, the more it can absorb. So I mentioned again the color of oil. You can remove red color or you can remove green color. Carotenoids and chlorophyll. So what are the benefits of bleaching? You remove the color bodies. You reduce trace metals as well. These heavy metals, calcium, magnesium, iron, and sodium. You reduce the non-hydrolyzable phospholipids. You can also remove the decomposition products, aldehyde, ketones, polymers, and non-triglycerides. And what are the absorbents that are used? Neutral bleaching earth, or clay, which is Fuller's earth, or it can be activated processed clay, it can be activated charcoal, or it can be silica. And you can also mix some of that up. Sometimes people use activated clay with bleaching earth as well. Okay, the dry bleaching system. Once it is already washed and vacuum dried, you feed it to the bleacher, and then you add the bleaching earth. So it can be activated or neutral, and then activated clay is usually more effective in removing color bodies and trace metals. Yeah. Okay, this is a dry bleaching earth system. What does it comprise of? You would have let's follow the flow. All in, heat up with plate heat exchangers, and then it goes into the vacuum at 50 torr, yeah, and you feed in the bleaching earth, and then after that you will filter it in this case leaf filters, and then the spent clay is taken out, then polishing filters to make sure that it doesn't pass on into the oil for the next set. Yeah. Okay. And then it is cooled before it goes out. Alright, so then the cyclone to recover any oil that they need. Yeah. Okay. So this is the process of it, and the oil is finally cooled to 40 degrees. The wet system is quite similar. How do you make it wet? What it does is it keeps the bleacher at a higher pressure, 667 bar, so that the moisture content is 0.2 to 0.4. Yeah. Now they have found that by doing this in some cases, the clay is better, efficiency of the clay is better, and the usage is lower. So otherwise, it's almost the same as the dry bleaching process. So you leave it for contact for 20 to 30 minutes, and then after that, it leaves the vacuum reactor, enters the vacuum dryer, and the moisture is reduced to 0.1%. Yeah. So this is the wet bleaching process. I do remember that sometimes you use the wet bleaching process when you're trying to bleach and you're not successful, and you try and do this, it seems to work. All right. Now the vacuum bleacher is just a pressure vessel there, and with what do you call it? 3 to 4 baffles inside here. You can see the baffles. Top entering agitator. The axial agitator pushes the oil down. The radial blade pushes it back up. Yeah. So the absorbent, mix it intermediate to get the absorbent and the oil get intermediate mixing. The baffles that are here prevent vortex formation, and then the mechanical mixer should have pumping capacity about twice in a minute, and you pump it around. Okay. So this is the vacuum bleacher. The bleaching clay is packed in from the top there, with an airlock, and you also add citric acid or phosphoric acid. Okay, filtration. Because of the continuous nature of most of the plants, the bleacher is normally equipped with two filters. So one in use and one on standby or being cleaned. Yeah. So you can automate it with the cycles, and it is very clear. It is very important that the oil is very clear of the clay and earth, because it will affect your deodorization afterwards. So these are pictures of a few of the filters. This is a plate and frame. This is a vertical leaf filter, and this is a horizontal leaf filter. Yeah. All right. So you have to choose the one that is most appropriate for you. Okay, physical refining. Now I've taken the picture from the right side from AOCS library. Yeah, and physical refining helps to lower the phospholipids level to a lower level. The bleaching removes remaining phospholipids, trace metals, and decomposition products, and FFA monoglyceride decomposition is removed. So there is the degumming process, there is the bleaching process, and finally both the deacidification and deodorization takes place in this final process. Yeah. So sometimes, if you look at literature, sometimes they just use the word deodorization, and actually they mean both deodorization and deacidification. Yeah. So when you look at that, just look up for that. So this is deodorization is usually the very last stage of edible oils processing, and here you remove the odors and the flavors, yeah, so that the product is blank. It means no taste at all, no smell at all, and this takes place under vacuum at a pressure of about 1 to 8 millibar. So what happens in it? First thing is you dry the oil, you remove whatever oxygen there is and moisture, then you heat it up to 240 to 260 degrees. Then steam is added, and you blow steam through the oil under vacuum at 260 to remove the the orders, yeah, making use of the principle of partial pressures. Then citric acid is added at the final stage as a chelating agent for trace metals. Yeah. Okay. And then finally, cooling to room temperature for storage. I always remember citric acid because when I was running the physical refinement, always have to add citric acid at the end. If you forget to do that, you could be in trouble. Yeah. Okay. So that's a very important step. Okay. What's the function? It can reduce the free fatty acid level, 0.05, 0.03. Forum standard score for 0.82. Yeah. Remove all the smell compounds, which are aldehyde, ketones, hydrocarbons, lactones, alcohol. Yeah. Reduces the PV to 0. Any trace metals that's left, that's why you use the citric acid as a chelating agent. Yeah. So it is a very essential step and not substitute for bleaching up step. So that's why it's always emphasized to me the addition of citric acid at the end is very important. Sometimes we can increase the polymers, constitute dienes or other decomposition products. Yeah, this is because of the high temperature, and there can be also a very small but detectable increase in trans fatty acid content, depending on type of oil and deodorization temperature. You remember earlier today, Prof. Chan talked about trans fatty acid in partial hydrogenation, but it can also form trans fatty acid when you deodorize at high temperature. You have a chart there. Here it is. Yeah. So here you see, this is a transformation in 20 minutes at 260 degrees. And then here is a 18.1, 18.2, 18.3. And you can see canola, soya, sun, corn, cotton, and palm. So the longer the purple bars and also the unsaturation basically, the longer it is, the more trans fatty acid is formed. Yeah? So this is one place that trans fatty acid is formed. So you would also think that if you're frying your oils at very high temperature, you could be forming trans fatty acid as well. Yeah? Okay. So this is one place that trans fatty acid can form. So we got to take note of that. So the people who did the, what you call that, deacidification deodorization came out with a very novel design of a dual temperature deodorizer. So basically what they said is we'll have a short contact time section at 260 degrees, deacidification, and then after that the bottom part here is the deodorization for a longer time at the lower temperature. Yeah. So that's what they do. One thing I think I didn't mention here, but I think tomorrow will be covered for palm is that the red color, the keratin, is actually decomposed so that you don't get the red color anymore. Yeah. Okay, the quality of deodorized oil should be good. Organoleptic acceptability. That means odorless, clean, and light in color. That's the physical attributes. And I still remember that very well because one of my jobs as a young refinery manager was to taste the oil after lunch. So when it's 1 week, 1 month, 6 months, 3 months, 6 months, okay. When it reaches 12 months, it's terrible. Yeah? So that's a job. But later on, of course, you get more senior and get somebody else to do it. Okay. So the chemical attributes, low free fatty acid, low peroxide value, which is a measure of the oxidation, maximum antioxidants still remain in there, and less composition of decomposition products are formed, like ketones and aldehydes. This could be carcinogenic as well. Yeah. Okay. Now, there are 3 types of deodorizers: the batch, the semi-continuous, and continuous. So this is the batch one. So basically, it's just a vessel there. Yeah. Vacuum vessel, dish or cone heads. You have heating coils inside. You inject steam inside. Yeah. And then, yeah, that's it. You create vacuum there. Very simple to use. Yeah. All right. Next one is semi-continuous, and this is you actually have trays inside there, and they drop from one to the other, to the other, to the other. Yeah. Finally, this one is the cooling. This one is the heating of it as well. Yeah. And then here you remove the fatty acid, and this is of course the PFAD. Yeah. In the case of palm oil, yeah, fatty matter that is separated out. So this is the semi-continuous process. So it spends a certain time there. After that, it drops to the next one. Sorry, it will drop from here, then the next one drop here, and then the next one. Yeah. So this is semi-continuous deodorizer. So finally, of course, it is cooled before it goes out. And very important, somewhere here you will inject the citric acid. Continuous deodorizer. This one operates continuously. Instead of dropping on tray to tray, this will be a continuous one. Yeah. And I think our what do you call it? Our Petronas friends and so on will be more familiar with this for your oil and gas refinery. Yeah. Okay. So I don't want to explain this, but you can see that this is a continuous process. And one of the nice things about continuous process is you're going to see a lot of heat recovery. So what happens is the cold oil, the hot oil coming in will heat the incoming oil so that you try and recover as much heat as possible. Okay, so I think one of the things you like to do as operating the plant is you want to compare them. So let's just have a look at the three types of batch: semi-continuous and continuous. Suitability. This is for discrete batches, specialty products. Yeah. Here, semi-continuous for frequent changeovers. Yeah. And can only be used with deodorization. Continuous where you produce very, very large volumes and you don't have a lot of changeovers. Yeah. Stripping steam at a pressure of 2 millibar. This will use 3 to 4%. Semi-continuous 1 to 1.5%. And then continuous we use a lot less. If you use a pack column, even less. Okay. Production rate, well, quite little, 7 to 8 hours per batch. Yeah. 4 to 6 times that of the batch deodorizer for the semi-continuous, and 5 to 8 times more than the batch deodorizer. Energy recovery, usually none unless you use an economizer. Quite high, up to 65%. And in continuous one, very high, could be as high as 90%. Yeah. So the cost, this is very high. This is 30 to 40%, and this one is 10 to 20%. Yeah. So what I'm showing you here are probably the older ones, but they're still being used. Yeah. And sorry. Where was it? Okay. So one of the things I'm showing you is this the types of deodorization, physical refining that can be going on. Yeah. And you're going to have various sizes of plants, yeah, depending on what your need is. Okay, other considerations, all contaminants. There are actually a lot of contaminants that could be present in our oil. Yeah. So if you look at it, you get worried, and you start wondering, if I don't refine my oil, how? But can refining remove this contaminants? Most of it, yes. Yeah, but not all of it. So let's have a look at it. Yeah. Phthalates, plasticizers in plastics. Yeah. You know that your plastics have got what do you call it? Plasticizers in them. And when they leach out and so on, they find their way into oil. Not so easy to remove. And then there's PCB. You remember PCB or not? Your electrical equipment, use it as a cooling oil. Yeah. So how does it end up in our food then? What happens is that it goes in the rivers and goes in the sea, and then the fish take it. So it's present in fish oil. So PCB has been banned. But if PCB is present and you refine it with carbon, you remove the PCB. Okay. Dioxins, when you have fires and smoke, you will have dioxins. pH, copra. You know the coconut, copra, you used to dry it in the sun, that's one way. Sometimes they dry it in smoke houses. When you do that, you get the pH, okay? But that can be removed by refining. There's also pesticides that you use, yeah? Mycotoxins in peanuts. Remember the alpha toxin in peanuts? You can refine it and then remove. Trans isomers, I covered that. Tomorrow we will have this covered, yeah? Okay? And mineral oil also tomorrow, yeah? So we hear more about that tomorrow. I will cover that. So most of the contaminants can be removed by refining. But the question we should always ask, why should it be there in the first place, and we should avoid it rather than remove it. Yeah? Otherwise the people will think, oh, the refiners are Superman. Everything they can remove. Yeah? I'm sure the refiners here will tell us, rubbish in, rubbish out, right? Okay. Alright, some EHS considerations. Spend bleaching earth, avoid contact with air to avoid the risk of spontaneous combustion and high IV loss. Yeah? We may not experience so much here with our palm oil, but I still remember my first experience refining sunflower. After that, we didn't do anything with the bleaching earth, just caught fire. Yeah? Spontaneous combustion of the bleaching earth that was used for sunflower. We dropped the bleaching earth down and left it there. The fire started by itself. It was warm, fire just started. And you know, the bomba come, another big event, I remember it, of course. Yeah, okay. And that is also what Prof. Chan said about the polyunsaturated oils are easy to combust. After filtering also, you're not careful to combust. So after that, I experienced, after we finish, we pour water in. Yeah, okay. Yeah, where economically viable, use physical refining instead of chemical refining. Two things, you reduce water consumption. The other thing is you don't form the soap stock. Because the soap stock you have to recover using sulfuric acid, and then you get acid oil. Yeah. So it's better if you can to use physical refining. Recover and reuse the condensate from heating process. I know at least one refinery is doing this because he won the ICAME Palm Oil Award for saving energy. Yeah. Okay. And then identify opportunity for integration. As I point out to you, the continuous one has plenty of opportunity for integration. Connect the nitrogen supply to deodorizer so that oxygen can be reduced in the event of fire. Yeah. Alright, so this is quite useful and important. But bear in mind that once you have nitrogen supply to a vessel, when you enter the vessel, make sure that that line is disconnected and there's oxygen inside. Yeah, that's the downside of it. Okay? And this may be more so for a pack column because you can have spontaneous combustion. Yeah? Okay. I also had a bad experience. This is not with refinery, but with fatty acid distillation plant. Yeah? We cool it down. We're quite happy with it. Then the guys didn't close back the manholes. In the night, we caught fire. Not a very nice experience. Okay. So, although cold, but you see the problem is the probes are on the surface of the vessel. It doesn't go inside the pack column. So you don't know that it's still hot inside there. So, well, those are the things that you learn and you never forget because you're fire in your distillation column. Yeah. Okay, is there any more after this? Alright, just to conclude, refining is very, very important. You remove unwanted minor components and you want to cause the least damage in the process. You want to minimize your refining loss and minimize the loss of desirable components. Yeah, because in the oil, and tomorrow you might learn about the palm oil especially, it has a lot of minor components. Now, this one will be a message from the refiners to the supplier of raw oils. Yeah, it's dependent on good quality seeds. You must take the appropriate refining steps. And if you use use physical refining, you will minimize pollution and also get high quality fatty acids. But unfortunately, not all oils can be physically refined. Where you can, then you should physically refine it. Okay, I think that's the conclusion. That's the end of it.
Okay, thank you, Qua. Any questions for Qua? Any question?
Oh, many. Okay, the lady in front first.
In the developing process, you mentioned that the removal of non-hydratable phosphatides is through as you add your chemical, then you will convert it into the hydratable phosphatide. So is there any chemical reactions going on in this process?
I think there will be, but most of it is absorbed by the leaching after that.
Yeah, it's basically hydrolysis. Yeah, you cut down one of the fatty acid, then it become dye or mono, then it's easier to go with the water phase.
And thank you.
Yes.
That's my panel of experts.
Okay, thank you very much.
Okay, next question. Somebody present. Yeah.
Yeah, you mentioned some considerations on ESH. How much impact do you think that can make to current refinery processes, given certain targets that we are planning for 2030, 2050, in terms of water reduction, net carbon, net zero, and so on? How much impact do you think that can give? Or are there other technologies that you are coming up with in the horizon?
Let me answer the question about what can be done. Yeah, and maybe the technology one I'll leave to our speaker tomorrow. Any new technologies that are coming up? All right. Okay. So what can be done? One of the members of POP6 is running a refinery, and he's actually done a lot of small things in his refinery and recovered a lot of energy, from that. And one of the things that he won the ICABE award for was for a little spirally exchanger. This size only, spirally exchanger this size. All he did was put it on top of the tank, because all the tanks where the steam condensate goes in, you see a lot of steam coming out. He just put it on top there and recovered the steam. And he saved a few hundred thousand ringgit a year just by doing that, because he used it to generate hot water for his fractionation plant. And since this was on his own initiative, and what I'm very happy about is, okay, he win awards, but in order to win awards, he has to share. And he's been sharing everywhere. So I'm sure you heard of it already and you know about it. So there are a lot of things that we, as engineers, can do in our factory to improve it. Yeah. Okay. And at the same time, of course, we look for new ways of doing things and so on. Yeah. Which I think we can look at that. And also technology, which I leave for tomorrow.
Do you think there's enough motivation for the local universities to actually start working on this kind of solutions?
I pass to the expert to answer. Prof?
Well, I think definitely, I think the interest is there. But I think one thing is that industry also will need to engage the university more, and also share with us the problems that the industry is facing. I think one of the problems that I see in terms of this industry and university collaboration is that if these two parties don't talk to each other, we are not going to know what exactly the problems that the universities, the industry is facing, right? And of course, in academic, a lot of times, we are working on problems that may not exist yet in the industry, but those are the grand challenges and stuff like that. Has yet to be a solution yet. Yeah. So I think definitely, I think that could be, there'll be interest to solve problems, and especially when there's funding given to the university.
Yeah, I think that part is a very important part. The universities yeah, it's not self-funded. It has to spend it. And yeah, industry also has to be willing to help work with them to do these things. And then there's some investment in it as well. So I think that part is quite important. And also I think to realize that while we have high hopes on universities, you must also realize that not everything will also succeed. And allow
Research,
for that sort of,
there's no.
allow for that sort of thing to happen. So because a lot of times we are looking at trying to do research that will yield results very quickly. And they call the low-hanging fruits and so on. Yeah, but sometimes all the low-hanging fruits are gone. By the way, I heard the story about low-hanging fruits. Yeah, anyone of you heard of it before? The low-hanging fruits are very sour. It's the one on top that is sweet. Okay. All right. So part 2 tomorrow. Your answer will come for the technology providers. Yeah. Okay.
Okay.
Any more questions?
Questions?
Yes.
Acid washing, I think that's phosphoric acid and also citric acid.
Yeah.
So are there other acids that we use for washing?
Not in my experience, but that's old already. Any expert who can help me with that, other than phosphoric and citric acid or washing?
I think so far that these are the best acid in terms of most economical way of doing that.
I mean, you can use others like even EDTA, panic acid, and other food grade acid, but normally those are more expensive. So the cheapest one, I think, probably is the phosphoric, right?
Phosphoric and citric
Followed by
acid,
Citric acid.
And phosphoric is still more efficient in terms of the
For
dosage.
gummy, yes.
For the gummies, for the
Use
chelating,
less
use
now.
citric
Yeah,
acid.
yeah.
It's used less phosphoric. Citric, you have to use higher concentration.
Mm.
Any other expert view? Yeah. Okay. Okay, I got a very good panel. Any more questions before quiz? My questions are very simple. I expect you to score 100%.
Okay. Only 2 questions, right?
Yeah, only 2 short questions.
Okay.
After this, can go home.
Now we got price presentation first.
Oh, yes. Any more? 30, 26. Coming. Okay. Hey, ciao already. Okay lah. Hey, come back. Okay. Okay, so this question is partly a trick question, but partly to emphasize that the size of plants have been growing bigger and bigger and bigger, and this is not the end of it. It will still grow bigger and bigger. But I do emphasize the fact that these are for commodity oils. Yeah? So those that I showed to you about the batch processes and so on, they're still there because not everybody is selling commodity oils. Somebody has to receive it at the end and turn it into the products they want and so on. But what is important is it's becoming bigger and bigger. Even as I put this figure out, you'll find somebody has a plant that's bigger than this. But what it means is that for this bigger and big plants, is that you're going to see efficiencies coming up. And as we ask anything in the savings, I think the energy savings will be coming in, the yields might be going up, that sort of thing. So that's one of the things that could help in efficiencies as the size of the plants grow bigger and bigger. Especially when you're operating a single stream and so on. As you change and then it becomes a bit more problem. So that's the answer there. But I'm only getting 43%. Let's see, 13%. 8. What is the 8? 8 is at 150. Right? Yeah, that's a bit small, I would say. Yeah, for commodity oils. Yeah. Okay, next and the last question. That's the last question. Easy quiz. I was hoping to get 90%. I still don't get it. Yeah. Okay. Again, it's meant to be a trick question. Receipt. No lie, cannot lie. Again, it's meant to be a trick question because one of the things that we have been educated in is to see anything that's light in color is good. Yeah. So if you go very far back, I like to look at the history of oils. So if you look back at 1911, when Procter & Gamble launched the Chris Crow brand, it was actually made from cottonseed oil. And cottonseed oil was dark green in color, terrible smell, nobody likes it. So what they're able to do is that they hydrogenated it, they bleached it, deodorized it, and it was a very light, white shortening. So everybody was happy with it. But what happened in the end? There's trans fatty acid inside it. So light color doesn't necessarily show that it's healthy oil. Yeah. Okay? So, but we are under the impression that the light color oil is a good oil. So all of us expect that. So one of the issues we also have with palm oil is that we want it to be very light in color. So we do all we can to make it as light as possible. And there are issues, and those of you in industry know that's coming up as a result of that. Yeah? So maybe that'll be addressed tomorrow. So this is in a way a trick question that not necessarily the lightest looking oil is the best oil or the most nutritious. Yeah? In fact, some of the oils that retain the color could retain some of the minor healthy components inside there. Yeah? So that's the quick trick question there because of the way we've been told anything that's light in color is good. Yeah? Alright, so that's a specific question. So it's my fault for not getting 100%. Okay, thank you very much.
All right, thank you, Qua. Thank you. Round of applause. All right, this brings us to the end of today's program. Just to sum up, I think today we have covered 5 modules. We start with oil and fats market, and we have oil and fats chemistry, and then we have covered upstream processes, so oil extractions, and refining is the midstream. So tomorrow we got another 5